In this video, we're going to go through some example exam-style questions for buffer calculations. Okay, so a buffer system was made by dissolving 5 grams of sodium ethanoate in 175 centimeter cubed of 0.250 mole per decimeter cubed solution of ethanoic acid, and we're given the Ka of ethanoic acid of 1.74 times 10 to the minus 5. Calculate the pH of the buffer system formed. Well, the first thing we should do when tackling a question like this is actually work backwards. We're being asked to calculate the pH of the buffer. Well, we know that pH equals minus log to the base 10 concentration of H plus ions. So what we really need to do here is find the concentration of H plus ions in the buffer system. To do that, we can use the Ka expression for a weak acid. Ka equals concentration of H plus times concentration of A minus divided by concentration of HA. Now we can rearrange this expression for H plus by saying concentration of H plus equals Ka times concentration of HA divided by concentration of A minus. Now in this specific question, HA equals our ethanoic acid, CH3COOH, and A minus ions, ethanoate, CH3COO minus. So for the workings in the rest of this video, I'm just going to refer to them as HA and A minus to make things a bit easier to write. But if you get a bit confused, just remember that HA is CH3COOH and A minus CH3COO minus. Now in the question, we're told the Ka value of ethanoic acid, 1.74 times 10 to the minus 5. So we know that isn't a problem. For these kind of questions, we can also assume that the concentration of acid at equilibrium in the buffer will be the same as the concentration of acid at the start. So in this situation, 0.250 mole per decimeter cubed. So we also know that value. Now, strictly speaking, that is an assumption. There will be a little tiny bit of acid dissociation that takes place, but the level of dissociation will be very small, so we can simply assume that the concentration of acid at equilibrium in the buffer is the same as the starting concentration of acid. Great, so this means all we need to find then is the concentration of A minus. Now this concentration of A minus is going to come from the sodium ethanoate that's added at the start. Because when you add solid sodium ethanoate to water or a solution, the solid dissolves and breaks apart, releasing ethanoate ions, CH3COO minus, and Na plus ions. Well, the CH3COO minus ions here are the same as the A minus in our expression. In other words, they're the conjugate base of the ethanoic acid. This means if we know the moles of CH3COO minus ions added, we can find the concentration of them, and this will be the concentration of A minus in the expression. Now the moles of CH3CONA added at the start will be the same as the moles of CH3COO minus present in the buffer. So we're told we've got 5 grams of sodium ethanoate. So the moles of sodium ethanoate added at the start, so moles of CH3COONA equals M over MR, with the mass being 5.00 grams and the MR being 2 times 12 plus 3 times 1 plus 2 times 16 plus 23, giving us a mole value of sodium ethanoate of 0.0609. Now this will be the same as the moles of CH3COO minus because it's a 1-to-1 ratio. So this means the moles of CH3COO minus equals 0.0609, okay? And we know that this is A minus, so the moles of A minus equals this value. Well, to find concentration of A minus, all we now need to do is divide the moles by the volume. So 0.0609 divided by 175 divided by 1000. Note we're using 175 here for the volume because we're told at the start we've got 175 centimeter cubed of solution, and we're dividing by 1000 to get the volume into decimeters cubed. This gives us a concentration of A minus of 0.348 mole per decimeter cubed. Great, we now have all the values we need, so we can tick for the A-. So to go back to this expression, all we need to do now is concentration of H plus equals Ka times concentration of Ha divided by concentration of A-. The question tells us that the Ka value is 1.74 times 10 to the minus 5. The concentration of Ha, we were told, was 0.250. And we've just calculated the concentration of A- to be 0.348, giving us a concentration of H plus ions of 1.248 times 10 to the minus 5 mole per decimeter cubed. Now we can use this concentration of H plus ions to find pH, because remember, pH equals minus log to the base 10 concentration of H plus ions, which equals minus log to the base 10, 1.248 times 10 to the minus 5, which gives us a pH value of 4.90. Great, part A is complete and answered. Now on to part B. A student then adds 5 centimeters cubed of 0.1 mole per decimeter cubed sodium hydroxide to the buffer. Calculate the pH change that occurs. Well, to answer this part of the question, we should remind ourselves what actually is happening in a weak acid buffer system. We've got an equilibrium established between Ha, the weak acid, H plus ions, and A minus ions, the conjugate base of the weak acid. Now, if OH minus ions are added to this system, they will combine with H plus ions, forming water. So OH minus plus H plus goes to form H2O. Now, in response to this, the position of equilibrium for the HA dissociation will shift to the right. More HA will dissociate, replacing the H plus ions that have reacted with the hydroxide ions. This will mean that the moles of HA decrease and the moles of A minus increase. And they actually decrease and increase by the same number of moles of OH minus ions added. So what we need to do is find out how much these change by. Well, the moles of OH minus ions added is going to equal concentration times volume from our sodium hydroxide solution. So the concentration is 0.10 and the volume is 5 divided by 1,000. Remember, divide by 1,000 to get it into decimeters cubed. This gives 5 times 10 to the minus 4 moles of OH minus ions. This means the moles of HA decrease by 5 times 10 to the minus 4, and the moles of A minus increase by 5 times 10 to the minus 4. Now at this point, there's several different ways you could represent your workings, but I think it's quite neat if we remind ourselves we have our HA going to H plus and A minus, and at the start here, now our starting moles of HA we can calculate using the initial concentration of the acid, which was 0.25, and the volume was 175 divided by 1,000, which gives us a starting moles of 0.04375. The starting moles of A minus we calculated earlier from the dissolved sodium ethanoate, and this was 0.0609. Now we've just said that the change in moles of HA is going to be minus 5 times 10 to the minus 4, and an increase in 5 times 10 to the minus 4 for A minus because of the hydroxide ions we just added, giving us a final moles in our new equilibrium system of 0.04325 for the HA and of 0.0614 for the A minus. Well, we're going to need these in concentration form for our Ka expression again, so the concentration is going to be moles divided by volume, so 0.04325 divided by the volume, which is now 180 divided by 1,000, because remember we've added 5 centimeters cubed of sodium hydroxide solution to our starting 175 centimeter cubed buffer solution. So That gives us a final concentration of HA of 0.240 mole per decimeter cubed. And for A minus, 0.0614 divided by 180 divided by 1000, which gives us a final concentration of 0.3415 mole per decimeter cubed. Looking good. All we need to do now is put these values back into our Ka expression to find concentration of H+. Remember, we said concentration of H+ equals Ka times concentration of HA divided by concentration of A-. The Ka of the acid hasn't changed, it's still an ethanoic acid buffer system, so 1.74 times 10 to the minus 5 times the concentration of HA, which we've just said is 0.240 mole per decimeter cubed, divided by the new concentration of HA, which we've just calculated to be 0.3415 mole per decimeter cubed, and this will give us a concentration of H+ ions of 1.222 times 10 to the minus 5 mole per decimeter cubed. Well, now we just need to put it back into our pH expression. So pH, remember, equals minus log to the base 10 concentration of H+ ions, which equals minus log to the base 10, or 1.222 times 10 to the minus 5, which gives us a pH of 4.91. But remember, there's a nasty little twist here, because the question actually asks us to calculate the pH change that occurs. Well, the initial pH we calculated at the start to be 4.90. This final pH we've just calculated to be 4.91, so the change in pH equals 4.91 minus 4.90, which gives us positive 0.01. The pH is increased by 0.01. A very small value, but that's kind of what we'd expect, because we're adding a small quantity of sodium hydroxide to a buffer solution. Really well done if you've made it through this question. There's lots of steps of work in here, and I've tried to explain each step rather than simply write out the answers. For a more condensed form of workings and some other practice questions to have a go at, please check the links in the description below for a buffers worksheet. Okay, another question. A student mixes 50 centimeters cubed of sodium hydroxide solution and 75 centimeter cubed of propanoic acid. Calculate the pH of the buffer solution formed. Well, the first thing we need to ask ourselves in this question is what happens when sodium hydroxide reacts with propanoic acid. Now, to make things easy with our workings here, we're just going to treat propanoic acid as a general weak acid. So HA is going to mean CH3 CH2 COOH. It's just a bit easier to write it in your workings and keeps things a bit clearer. But the weak acid in this question is CH3 CH2 COOH. So when HA, or a weak acid, reacts with OH minus ions, it forms A minus and water. Now, the A minus in this situation is going to be a propanoate ion, the conjugate base of the propanoic acid. So there's a few different ways we can represent the workings at this stage, but this is the way I like to do it so we can see what's going on. So the starting moles of HA is going to equal concentration times volume. Well, the concentration of the acid we're told is 0.80. The volume of the acid is 75 centimeters cubed, so 75 divided by 1000 to get it into decimeters cubed, which is going to give us a moles of HA of 0.06. Same idea for the moles of OH minus ions coming from the sodium hydroxide. The concentration is 0.5. The volume 50 divided by 1000, which gives us moles of OH minus ions of 0.025. Now, we can see here that the OH minus ion is the limiting reagent, which means all of the 0.025 moles of OH minus ions are going to react with the HA. So the change in moles of our HA is going to be minus 0.025, and obviously minus 0.025 for OH minus ions, but this is going to make 0.025 moles of A minus because it's a 1-to-1 ratio, making the A minus. This is going to give us a final moles of HA in the buffer system of 0.035, OH minus aren't 0, and A minus 0.025. Great, so this is what happens when the sodium hydroxide reacts with the propanoic acid. The next thing we need to consider is how to calculate pH. Well, pH equals minus log to the base 10 concentration of H+. So we need to calculate the H+ ion concentration to find the pH. To do this, we can use the Ka expression of the weak acid, so Ka equals concentration of H+ times concentration of A- over concentration of HA, which we can rearrange to give us concentration of H+ equals Ka times concentration of HA divided by concentration of A-. Well, to convert these mole values of HA and A- we've just calculated here into concentration, all we need to do is divide by the volume of the solution. So the final concentration equals moles divided by volume. Well, in this situation, for the HA, we're going to divide the 0.035 moles by the volume, which is 50 centimeters cubed, add 75 centimeters cubed, because remember we're mixing the two solutions together, and we're going to divide by 1,000 to get it into decimeters cubed. This is going to give us a final concentration value of 0.28 mole per decimeter cubed. Same idea for our A-, we're going to divide this number of moles by the same total volume, so 50 plus 75 divided by 1,000, which gives us an A- concentration of 0.20 mole per decimeter cubed. So now all we need to do is substitute these values here into our expression here for HA and A-. So to find the concentration of H+, we just need to substitute our values. So the Ka, we are told in the question, is 1.35 times 10 to the minus 5. The concentration of HA we've just calculated to be 0.28, which is here, mole per decimeter cubed, and we're going to divide this by the concentration of A-, which we've just calculated to be 0.20 mole per decimeter cubed, giving us a final concentration of H+ ions of 1.89 times 10 to the minus 5 mole per decimeter cubed. Well, we said earlier on that pH equals minus log to the base 10 concentration of H+, so minus log to the base 10, 1.89 times 10 to the minus 5 gives us a pH value of 4.72. Great! Part A of this question is complete. We've calculated the pH of the buffer solution formed. Now part B of this question is if 7.5 centimeter cubed of HCl is then added to the buffer, what is the new pH of the solution? Well, to tackle this part of the question, we need to ask ourselves what actually happens when we add H+ ions to our equilibrium mixture of HA going to H+ and A-. Now, if HCl is added, what we really do is we add H+ ions because the HCl dissociates to release H+ ions. Now, if we increase the moles of H+ here, the position of equilibrium will shift to the left. So more A- will combine with H+ to form HA. This will decrease the moles of A- and it will increase the moles of HA. Well, the moles of H+ added will be the same as the moles of HCl added. So moles of H+ added equals concentration times volume, which equals 0.1 times 7.5 over 1,000, which means we are adding 7.5 times 10 to the minus 4 moles of H+. So this means the change in moles of HA is going to be positive 7.5 times 10 to the minus 4. And the change in moles of A- is going to be negative 7.5 times 10 to the minus 4. because remember the A- combines with the added H plus to make HA. Well, our starting moles of HA we calculated earlier to be 0.35 moles of HA and A- 0.025. So 0.035 moles of HA and 0.025 moles of A-, meaning our final moles of HA will be 0.03575 and our final moles of A- will be 0.02425. Now, to find the concentration of H plus ions in our solution for pH, we know we're going to need to use the expression Ka equals concentration of HA divided by concentration of A-. So we need to convert these mole values of HA and A- to concentration. To do that, we're going to divide number of moles by volume. So 0.03575 divided by 132.5 divided by 1,000. Notice the volume is now 132.5 because it was 125 centimeters cubed and we've just added 7.5 centimeters cubed of the hydrochloric acid solution, giving a total volume of 132.5. This gives a final concentration of HA of 0.2698 mole per decimeter cubed. Same for A-, we're going to divide the moles by 132.5 divided by 1,000, and this gives us a final concentration of A- of 0.183 mole per decimeter cubed. Well, to find concentration of H+, remember, all we need to do, concentration of H+ equals Ka times concentration of HA divided by concentration of A-. Well, the Ka value of our acid hasn't changed. It's still 1.35 times 10 to the minus 5 times our concentration of HA, which we've now just calculated to be 0.2698, divided by our concentration of A-, which we've also just calculated to be 0.183, giving us a concentration of H+ ions of 1.97 and a few more decimal places which we'll carry through, times 10 to the minus 5 mole per decimeter cubed. Great! All we now need to do is use our good old friend pH equals minus log to the base 10 concentration of H+ ions, which gives us minus log to the base 10, 1.97 times 10 to the minus 5, which gives a pH of 4.70. Phew! Well done. Okay, and another one. A student needs to make an acidic buffer with a pH of 5.1. They are provided with 100 centimeters cubed of 0.5 mole per decimeter cubed ethanoic acid and solid sodium ethanoate. What mass of sodium ethanoate should they add to the acid solution to form the buffer? And we're given the Ka of ethanoic acid here. So like all acidic buffer calculations, we need to consider the Ka expression for a weak acid. Ka equals concentration of H+ ions times concentration of A- ions divided by concentration of HA. Now here, the HA, the weak acid, is ethanoic acid, CH3COOH, and A- is an ethanoate ion, CH3COO-, the conjugate base of the ethanoic acid. We are told the value of Ka, 1.74 times 10 to the minus 5. We are told the concentration of ethanoic acid, 0.5 mole per decimeter cubed. And we're actually told the concentration of H+, because we're given a pH of 5.1. Now remember, concentration of H+ equals 10 to the minus pH. Great, we know all three of these things, but what we don't know is the concentration of A-, the ethanoate ion. Now we can rearrange this Ka expression to give concentration of A- equals Ka times concentration of HA divided by concentration of H+. And once we know the concentration of this A- ion, we can figure out the mass of sodium ethanoate that should be added to give this concentration. because the sodium ethanoate dissociates to release ethanoate ions. So let's substitute the values in. Well, the Ka value is 1.74 times 10 to the minus 5. The concentration of Ha is 0.50, and the concentration of H plus is going to be 10 to the minus 5.1, giving us a concentration of A minus of 1.095 mole per decimeter cubed. So now we need to figure out what mass of sodium ethanoate do we need to add to the solution to give this concentration of A minus. Well, first of all, let's figure out the moles of A minus we need to give that concentration in this volume. So moles of A minus equals concentration times volume. Well, we've just said that the concentration is 1.095, so 1.095. The volume of the solution that we need to end up with is 100 centimeters cubed, because we're adding the solid to 100 centimeter cubed of solution. So times 100 divided by 1,000. We have to divide by 1,000, remember, to get it from centimeter cubed to decimeter cubed. And this gives us the moles of A minus present as 0.1095. So now we know the moles of A minus that we need to add to this system. Well, remember, we've already said that the moles of A minus come from the sodium ethanoate. Sodium ethanoate, CH3COONA, when added to water or a solution, dissociates and splits apart into CH3COO- and Na+. Well, this here, CH3COO- is our A- for the ethanoic acid, and it's a 1-to-1 molar ratio of sodium ethanoate to CH3COO-. Now this means that the moles of A- equals the moles of sodium ethanoate. Well, to figure out the mass of sodium ethanoate then, we can use mass equals N times mR, and the moles in this situation is 0.1095. The mR, or molar mass of sodium ethanoate, is 2 times 12 plus 3 times 1 plus 2 times 16 plus 23. That's just adding up all the relative atomic masses of the atoms in the formula. This gives us a total grams of 8.98, meaning 8.98 grams of sodium ethanoate need to be added to the ethanoic acid to give the buffer system a pH of 5.1.